Okay, so let's continue with our chapter of electric current. So from the previous video, we stopped at the mechanism of the conduction of electricity through a wire. Okay, so let's refer back to the previous lesson that we learned. So the mechanism of conduction of electricity in metals. Okay, so for the first step, the potential difference is supplied across A and B, so the electric field is produced. So the E is basically the potential difference divided by the length of the wire. Okay, so when the electric field is produced, then the free moving electrons inside the metals are accelerated due to the electric force. Okay, so accelerated free moving electrons for the third step will collide with the lattice atoms. Then the net velocity is well known as drift velocity. So the collision of the between the free moving electrons and the lattice atom will cause the velocity of the free electrons to be decreased. So that is why that is the net velocity when before and after the collision between the free moving electrons and the lattice atoms, and hence the drift velocity will produce the net flow of charge. So this net flow of charge is also well known as electric current. So the drift velocity of the free electrons is always opposed the direction of the electric field. So this also same goes to the electric current. So the free electrons at the same time opposite direction to the electric field and also opposite direction to the electric current. Okay, so the fifth statement is about the net flow of charge will produce the electric current, which is opposite direction to the flow of free moving electrons. Okay, so there's another note need to be understand that, which is the okay, so let me just write it down first. Okay, slow. Okay, let me just zoom it in. Okay, slow drifting electrons in the motion sorry is the motion that produces the electric current instead of random motion. Produces electric current instead of random motion. Okay, so this is actually an important note need to be reminded, which is the drift velocity is the one that will produce electric current, which instead of the high speed and the random motion of free electrons when the power supply is not connected to the wire. Okay, so this is the random motion. Alright, so this is the first notes need to be reminded. Okay, alright, so the next part is about how can the drift velocity produce the electric current at the instance. Okay, so although we know that when the drift velocity is very small, but how can the I, which is the electric current, be produced at instance? So this is our questions. At the instance. Okay, so we know that the drift velocity is actually very small, which is the net velocity after colliding with the lattice atoms. And the question is, how can the electric current can be produced at the instance? at the instance of time when, okay, so for the example, if we are going to open the light, the switch of the light, at the instant when we open the switch of the light will instantly turn on, is it? So how can the eye, the question is, how can the eye be produced at the instance of time in such as in less than, I say less than 1 seconds? Okay, so this is our concept, which I use the red pen. Okay, so although the drift velocity is very small, but the effect of the current is felt instantly. So the effect of the current is actually felt instantly, such as if we open the switch, the light will directly turn it on. Okay, so when the current is turned on, when the current is turned on, since, okay, so this is the key that that will answer our questions. Since all free electrons in the current, in the circuit, not the current, in the circuit are moving at the same time. So this basically explaining about all the free electrons in the circuits are actually moving at the same time. So that is why we can feel that the current is felt instantly when the switch is turned on. So this one should be the switch, not the current. When the switch is turned on, since all the free electrons in the circuits are moving at the same time. So although the drift velocity is small but the free electrons are moving at the same time. So this will give us an instant electric current. Okay, so let's move on to the next part. Okay, so there's actually another questions. So my question is, when we open the circuit for for a long time, such as 1 hour, 2 hours, then we will feel the temperature of wire is keep increasing, right? So my question is, why the temperature of the conductor will increase? The temperature of the conductor is increased. So this is our questions. Okay, so let's say I have my wire. Okay, so if my electric field is supplied from the left to the right, okay, so basically my electrons will move from the right to the left. Okay, so the accelerated electrons will basically collide. So this actually is colliding with the atoms. So this is the atoms, or I can say it is an ions. Okay, so colliding with the atoms or ions. So the collision will causes the energy. Energy is transferred. Energy is transferred from electrons to the lattice atoms. So this basically is related to the our previous knowledge, which is from the chapter of the heat transfer. So the energy is actually transferred from the electrons to the lattice atoms. So the energy that transfer to the atoms, so this atom will eventually begins to collide, so the collision with larger amplitude and collide with the neighboring atoms, so hence the energy is transferred throughout the wire. Okay, so this is the knowledge which from the chapter of heat transfer. Okay, so in the full sentence, okay, let me just write in the blue color. So when the potential difference, so my potential difference is V applied across the conductor, these electrons collide with the lattice atoms. Okay, so I should write as the positive ions, which is more accurate since all the atoms lose the electrons. Okay, so collide with the positive ions. Positive ions. Okay, energy. Okay, let me just see for a while. Energy of the electrons. Energy of the electrons. Okay, so this is our keywords. Is transferred. So as I said just now, the energy is transferred from the electron to the lattice atoms or the positive ions to the positive ions and cause the ions to vibrate vigorously. Cause the ions to vibrate vigorously. Okay, so hence the heat energy is transferred. The heat energy is transferred. Okay, so this is the reason why the temperature of wire is increased when the current is allowed to flow for one not over 1 hour. I should say that for a few minutes later, the temperature of the wire will eventually increase. Alright, so we have done for this subtopics. So let's move on to the new subtopics, which is called, okay, so let me just find. Alright, so let's just move on to the, okay, there's no space here, so I just write it here. Okay, I just write it here. Alright, so Wait for just for a moment here. Okay, here. So let's move on to our drift velocity. So we all know that the drift velocity is actually the net velocity of the electrons after colliding with the lattice atoms. Okay, so the definition for the drift velocity is actually, okay, so let me just how should I describe the definition for the drift velocity? Okay, so just for a moment here. Okay, so defined as, so the drift velocity is actually defined as the net velocity of the free moving electrons free moving electrons after colliding with the positive ions. Okay, so the drift velocity is actually, okay, the symbol for the drift velocity is the v bar, okay, which is defined as the net velocity, which of course opposite direction to the electric field, since the electrons is moving with which opposite direction to the electric field. Okay, so defined as the net velocity of the free moving electrons after colliding with the positive ions. So this is the definition. Okay, so for the next part, we're going to find out what is the relation between the electric currents, okay, between the electric currents and the drift velocity. So in order to find out the relation, we need to derive a formula. Derivation of I is actually equals to NE V bar A. Okay, so let me just draw a wire. Okay, so let's say this is our A and this is L, which is the length of the wire. Okay, so my I is actually flows from the left to the right. Okay, so basically if the I is from A to B, hence my free moving electrons is actually moved from B to A. Okay, so of course the free moving electrons move with the drift velocity. Alright, so first of all, we know that the volume for the wire is always equals to the cross-sectional area times or multiplied by the length. Okay, so from the previous video, we did talk about the free electrons density, okay, which is also known as the number of free electrons, number of free electrons, per unit volume. So the number of free electrons per unit volume, which is N, is actually equals to the rho Na over molar mass. So this is the number of free electrons per unit volume. So if I wish to find out, so if I wish to find out the total free electrons inside the wire, so what I need to do is actually multiply the number of free electrons per unit volume multiplied by the volume of the wire. Okay, so total number of electrons, not electrons, should be free electrons, sorry, my mistakes. Total number of free electrons in the wire. Okay, so in the metal wire, more specific, so which is equals to the n times, okay, n times the AL. So this AL is the volume, and this N is the number of free electrons per unit volume. Okay, so if I wish to find the total charge which possessed inside the wire, so the total charge, not total charge, total electrical charges, which is more precise, total electrical charges in the conductor. So conductor and wire are the same. In the conductor, okay, so if the electrical charges, the number, okay, how should I say that? The higher the number of free electrons, the higher is the electrical charges. So I can conclude that my Q is actually directly proportional to the free electrons, the total number of free electrons. Okay, so is it correct? Sorry, I think this relation is wrong. Okay, so the higher the number of free electrons, the higher the quantity of electrical charges. This is because the electron is the one that carry electrical charges. Okay, so my Q is actually equals to the total number of free electrons inside the wire. Okay, so my electrons must multiply by the total number of free electrons inside the wire. Okay, which is NaL. So NaLe. Alright, so this is the total electrical charges in the conductor. Okay, so at the beginning of the part, at the beginning of the chapter, we did discuss about the relation between the electrical charges and the electric current, which is Q is actually equals to IT. So if I about to equating the both equation, so what I get is actually IT is equals to NaLe. So if I move the T to the other side, what I get is actually this one. Okay, so NaE, and so we know that this L is actually represent the distance of the free moving electrons. So this is the time taken for the electrons to move from one point to the another point. So L over T basically will give us the drift velocity. So if I arrange in the form that I remember, which is NE V bar A. So this is the relation between the electric current and the drift velocity. Okay, so alright, so we have done for the drift velocity. So let's move on to some example of the questions. Alright, so I think I just write it here. Okay. Okay, I think I just write here. Okay, so for the examples, so for the first examples, so let's say I have my copper wire. So the copper wire, so the total not total, number of free moving electrons per unit volume, which is given as 8.46 times 10 to the power of 28 per meter cube. So, and the diameter of the copper wire given as 0.025 millimeter. So the millimeter what we get is actually times 10 to the power negative 3 meters. Okay, so the I possessed by the copper wire, which is 3.0 ampere. Okay, so the question is, what is the drift velocity inside for the free moving electrons? So what we need to do is actually apply directly the formula that we learned, which is NeV bar A. So this is 3 and this is 8.46 times 10 to the power negative, not negative, 28. Okay, so electrons is 1.60 times 10 to the power negative 19. Okay, so the drift velocity that which is the one that we need to find. Okay, so since the wire is in the cylindrical form, not the wire, sorry. Since the cross-sectional area is in the circle form, so this is the cross-sectional area. So hence we consider the cross-sectional area is a circle. So the area for the circle is actually pi r square. Pi r square. So this is pi and r is the half of the diameter. So 0.025. Okay. 0. Okay. Times 10 to the power negative 3 divided by 2. So this is square. So finally what I get for the drift velocity is, okay, let me just find for a second, 4.51 times 10 to the power of negative 3 meter per second. So the SI unit for the drift velocity is is also known as meter per second, same as the normal velocity that we learned. Okay, so this is we have done for the first questions. Okay, so let's move on to the second examples. So consider I have the two copper wires. So my two copper wires, basically we have X and Y. So we have copper wire X and copper wire Y. Okay, so the diameter of the copper wire Y is actually twice the diameter of copper wire X. Okay, so this is the first information. Okay, so the question is, what is the ratio of the drift velocity x to the drift velocity y? Okay, so this is the question. Okay, so from the from the information given and the question that asked by the questions, okay, so we know that there is actually one relation that included both quantities, which is I is actually equals to NE V bar A. So from here we have the drift velocity, and if we're about to find out the diameter, so what we need to do is actually derive this A. So this is the pi r square. So the pi r square, what we have here, so since d is actually d over 2 is actually r, okay, so what we need to do is actually derive this one. So this is d over 2 square. Okay, so if I derive the expression for the drift velocity, okay, so I just do it step by step so that you can see it clearly. Pi d square over 4. Okay, so 4i over ne pi, 4i over ne pi, 1 over d square. So what we get is actually v. Okay, so is it correct? So let me just check for a while. Yeah, the expression is correct. So from here I can see that my drift velocity is actually inversely proportional to the square of the diameter. So this is the relation. So from this relation we are able to find out what is the ratio of the Vx to the what is the ratio of the V bar x to the V bar y. Okay, so my V bar x to the V bar y. So since the relation is inversely proportional, so what I need to do is actually dx square and dy square. So both so the relation is in the inversely proportional condition. Okay, so from at the beginning of the question, the information did given us an important note, which is the diameter of y is twice the diameter of x. Okay, so what I need to do is actually substitute this one as 2 dx. So this is dx square. Okay, so vx over vy. Okay, so if I cancel out this, so this is dx square and 2 square, so finally what I get is actually 4. So this is the examples. Okay, so we have done for the drift velocity. Alright, so I think that's it. So okay, so I think we'll stop here now. So we'll continue the next other parts on the next video. So the time is quite long now. So if there is any question need to be asked, please comment below this video. So I'll see you next time. Thank you. Bye.